So let's take stock of where we are in our project. What we're trying to find out is, what is the efficiency of conversion of the potential energy stored in methane gas into electrical energy output from our generator. The energy that's stored in the natural gas is stored in the chemical bonds that join together the atoms that make the methane molecules. Combined with oxygen in the flame, that energy is converted into heat. That heat energy then goes into the water, and it begins to make the particles move around more, raising their temperature, means the particles are moving more. And as their kinetic energy increases and they become steam, they push their way through a hole. That force then turns a turbine attached to a generator, and that kinetic energy is converted into electrical energy. So we want to know how much of the energy that we started with did we end with? And we also want to know what's the startup cost. In order to get from here up to here, we have to put a lot of energy in before we can even make this generator spin. What's the startup cost? And we're going to look at this from one Bunsen burner's amount of heat and then two Bunsen burners amount of heat. So I did a little demonstration that was in the previous video and showed you what it looked like when I collected my data, and now I'm going to do the analysis part, the calculations. So the first step is I measured how much time it took to boil the water with just one Bunsen burner. And so a little bit of math here first. When you look at the timer, the stopwatch, it gives you minutes and seconds. We want to convert this all the way down to just minutes. So since there's 60 seconds in a minute, 3 minutes and 45 seconds is the same thing as 3 over 45/60ths of a minute. So if you do the math there, divide, it's 3.75 minutes. That's how much time it took to boil the water with just one Bunsen burner. So I'll use 3.75 minutes as my time, my startup time. Now when the generator started going, I measured the amount of electricity in volts and in amps. I drew how the needle looked, and when you look at the measurement scale that we're using, the 2-volt measurement scale on that meter is the one that's at the bottom here. Each little line is 0.1 volts. So if I measure 5 little lines, that means that there was 0.5 volts of electricity being generated while that generator was spinning. The amps, I pushed the 100 milliamp button and we measure that scale. It's the middle one. Each one of these lines is multiplied by 10, so this is really 10, 20, 30, 40, and so on milliamps. It was right in the middle here, 45 milliamps. If I convert that into amps, that's the same thing as dividing by 1,000 or moving the decimal point 3 places to the left, 0.045 amps. So when I was running the generator, I was making 0.5 volts of electrical potential and a current of 0.045 amps. So now let's put this into terms that we can compare, the input and the output. So how much energy does the generator make for each minute that it runs? Starting with the volts, 0.5 volts, times the amps, which was 0.045 amps, times 60, which is just part of our conversion factor here. I'll do the math. And so 0.5 times 0.045, oops, 0.5 times 0.045 times 60. 1.35 joules for every minute that I ran the generator. 1.35 joules of electrical energy. So that's the output. Let's compare that to the input. For every minute that the Bunsen burner is burned, it uses 1.0 liters of gas. You can look back a couple of my videos ago. There was a demonstration. I showed how I measured the amount of gas that comes through every minute that you turn on the gas. Every liter has a fuel capacity, a heat capacity of, a fuel value of 38,000 joules. That's a lot of heat that you can make when you burn each liter of gas. So if for every 1 minute there's 1 liter of gas, and every liter has 38,000 joules of heat, that means that there are 38,000 joules of heat energy being burned every minute that you have that gas jet on. So this is how much energy came out of the generator. This is how much energy went in to the Bunsen burner. There's a big difference there. We're losing a lot of the energy that we started with. We can look at that in terms of percent. So let's see what percent of the potential energy from the gas was converted into the electrical energy for each minute the generator was running. If there was 1.35 joules of electrical energy every minute, and this is how many joules were put in every minute, then we'll divide and multiply by 100 to make it a percent. 1.35 divided by 38,000 times 100 is a very, very small number. I'm going to put this into two significant figures. 0, let me double check my math here. 1.35 divided by 38, 1, 2, 3, equals times 100. Does it look a little bit high to me? There we go. 0.003536%. That is not very efficient. If all of the energy that I put in was turned into electricity, it would be 100% efficient. If only half of the energy that I put in was turned into electricity, it would be 50% efficient. But this is like 36 ten-thousandths of a percent. That's ridiculous. There's not very much of the energy being turned into electricity. Another way to look at this is to see, for every 1 joule of electricity that I make, how many joules of heat does it take? So I'll take my 38,000 joules of heat energy that I use every minute, and the 1.35 joules of electricity that I make every minute, and I'll divide 38,000 divided by 1.35. I'll round that to two significant figures. It's 28,000 joules. That is a lot of energy. That means that I have to spend 28,000 joules of heat energy just to make 1 joule of electrical energy. That's like spending $28,000 and only getting $1 in return. That's a huge loss. You wouldn't be able to make a profit in a business that way. So this is not a very efficient generator. It's not turning the energy from the gas into electricity very efficiently. What happens if you double the number of Bunsen burners, though? Does it make it more efficient? After all, you've got more heat, but also you're burning more gas. So are you getting more in return? Let's take a look and see what the results show. So, just to double check, when I measured the time that it took, the time was 2 minutes and 15 seconds, which is the same thing as 2 1/4 minutes. So I'll record 2.25 minutes. That's how long it took. We're going to use those values in a later calculation. The measurement for the volts was a little bit past the 1 volt mark. It was 1.1 volts. And for the milliamps, it was 100 milliamps, or 0.1 amps. So clearly more electricity was being made than before. Roughly, before it was 0.5 volts, now it's 1.1, so that's twice as much volts. Before it was 45 milliamps, now it's over 100, so it's clearly more than twice as many milliamps. So 2 Bunsen burners seems to be at least doubling the amount of electricity that's being made. Let's find out what the efficiency turns out to be. So if I had if I had 1.1 volts and I had 0.1 amps times 60, when I do the math, I get 6.6 joules for every minute that I'm running this generator. So that's more than I had before, but it's still not a whole lot. 2 Bunsen burners uses twice as many liters of gas every minute, so I'm going to put 2 there instead of 1. So if I had 2 liters burning for every minute, and this is how many joules are in each liter, then I'm going to have twice as many joules being burned every minute, 76,000 joules every minute. So I'm burning this much heat every minute, and I'm getting this much electricity in return. Still not a very efficient process. So let's calculate the percent. If I had 6.6 joules every minute divided by the 76,000 joules that I'm spending every minute, 6.6 divided by 6.6 divided by 76,000 times 100. Alright, so this is 0.0087% efficient. Still not very efficient, but more efficient than it was before. And if I do the other calculation, if I had the 76,000 joules that I put in every minute, and I get back 6.6 joules every minute in return, then what is my return here? 76,000 divided by 6.6. I'll round it to two significant figures. It's 12,000 joules. So now I'm spending 12,000 joules every minute to make 1 joule of electricity. That's better than it was before. It's more efficient, but it's still not a very efficient process. Having two of the Bunsen burners put more energy in, and I got more energy back. When I had just one Bunsen burner, it was only 0.0036% efficient, and it cost me 28,000 joules of gas heat energy to make 1 joule of electricity. Now with two Bunsen burners, it's more efficient, and I spend less energy to make each joule of electricity. So there's another aspect that we want to look at, and that's the startup cost. How much energy do we have to put in just to get this thing running? So here's where we're going to use our time data. Each Bunsen burner again uses about 1 liter of methane gas for every minute that it burns. And so we'll calculate how much energy it takes to actually heat up the water to boiling point, and then we'll look and see in the time that it took to boil the water how much energy was used. So we'll use the heat equation that we've used before. We'll solve for the quantity of heat. We need to know the specific heat capacity of water, 4.184 joules per gram degree Celsius. We need to know the mass of the water. The mass was 300.0 grams. That's how much you put into the can to boil. And you need to know the temperature change. The temperature change, we've got two temperatures, the starting temperature and the ending temperature. Room temperature is about 23 degrees in the room. And if we heat it up to 100 degrees, that's the boiling temperature of water, that would be a temperature change of 77 degrees. I found that by subtraction. So I'll put 77.0 degrees Celsius. Multiplying these together to find out how much heat was involved, times 300 times 77, and I'll round this to 3 significant figures, 96700 joules. That's how much heat it takes to get the water from room temperature up to boiling temperature. So that's my startup cost. That's how much I'm going to have to put in. How much did I put in compared to how much it really cost? Let's see if I spent more than I needed to. So for one Bunsen burner, the startup time was 3.75 minutes. And for every 1 liter per minute that comes through the gas jet, there are 38,000 joules of energy. So 3.75 times 1 times 38,000 joules. And I'm going to round this to 2 significant figures. So 140,000. That's how many joules of heat energy I have to put in. That's how many joules of heat energy I did put in when I ran the gas for 3.75 minutes. That's how much I needed. That's how much I used. So I needed less than I used. That means that some of it was lost or wasted. How much? Let's make a percentage. The heat needed to boil the water was 96,700 joules. I actually spent 140,000 joules. So I'll divide that. 96700 divided by 140,000 times 100. 69%. 69% of the energy that I put in was used to boil the water. The rest was used for something else. It was used to heat the can, it was used to heat the room, because some of the energy probably didn't go into the water, so the missing energy is our waste. 69% of the energy went into boiling the water. The rest was lost as waste. That was with just one Bunsen burner. Suppose I had 2 Bunsen burners. Well, I observed that it boiled faster, it took less time, so maybe I wasted less energy. However, this time I was using 2 liters every minute, and so when I do the math, let's see how much I spent. 2.25 times 2 times 38,000 equals, I'll round that to two significant figures, 170,000 joules. That's more. I spent more energy this time than I did the first time. With two Bunsen burners, I used more energy to get my water to boil than I did when I had only one Bunsen burner. That's interesting. So if I calculate what percentage of the energy was actually used to boil the water, so 96,700 joules divided by the 170,000 that I spent times 100, so 96700 divided by 170,000 times 100, 57%. So when I had one Bunsen burner, 69% of the energy was used to boil the water. The other 31% that's missing was wasted. Two Bunsen burners, only 57% of the heat was used to make the water boil. The rest of it was wasted. So I had 31% waste. This over here had 43% waste. So there's a big difference there between one Bunsen burner and two Bunsen burners. Clearly, two Bunsen burners is not the way to go. You waste more energy than with just one Bunsen burner. So let's summarize our findings here. When there was just one Bunsen burner, for every minute that I ran the Bunsen burner, 28,000 joules of heat energy went in for every 1 joule that I got back in electricity. That is a pretty lousy efficiency. That means from the flame to the electricity, I had an efficiency of 0.0036%. Most of the heat that was being produced in the flame must have gone somewhere else out into the room. That's one place where the energy might have been lost. There are other places that it could also have been lost, and you can think about where the energy is going through the process of converting from the potential energy to the electrical energy, and label the diagram that's in your packet to show where you think that energy might be going, where it's lost. One place definitely is out into the room. Another thing about this was that it took a lot of energy to get this thing up and running. For the one Bunsen burner, 69% of the energy went into the water to get it to boil, with a loss of 31%. So we have to account for where that other 31% went. Now when there were two Bunsen burners, it's a little different. For every 12,000 joules of energy input, we get 1 joule of electrical output for an efficiency of 0.0088%. More efficient, but still not very efficient at all. And with two Bunsen burners, how much of the energy actually went in to get this thing started? 57% of the energy went in to get it started, the startup cost. So less efficient startup cost, but more efficient conversion of energy into electricity once it gets started. Maybe the way to do this is to start the water boiling with one Bunsen burner, because that's more efficient, less energy is wasted, and then kick on the second Bunsen burner once it's up and started so that you can generate more electricity. That could be a way to improve the overall efficiency of the project, but that would require a little bit of coordination and extra steps. So there are some questions to answer looking at your data, and we'll take a look at those when we're back in class.